The leading cause of highway bridge failure in the United States is scour, defined as the erosion or removal of stream bed or bank material from bridge foundations due to flowing water. The Federal Highway Administration Bridge Scour Evaluation Program defines a scour critical rating as scour within limits of footings or piles, or scour below spread footings, bases, or pile tips. In the case of our bridge, unknown foundations create a higher risk for scour damage because the foundation depth is not known, making the determination of scour depths difficult. Our project is located in the town of Charlotte, Vermont, about 15 miles south of Burlington. The bridge is located at the intersection of Moncton Road and Spear Street and is approximately 30 minutes by car from the University of Vermont campus. It crosses Lewis Creek at the mentioned intersection and has an upstream drainage area of roughly 70 miles.
The Quinlan Bridge was entered into the National Registry of Historic Places in 1974. It is a Burr Arch-style wooden-covered bridge and has a capacity of 5 tons and a truck restriction. The bridge foundation is concrete capstone with an unknown foundation depth and wing walls extending into the stream. The stream has a strong meander and is causing significant erosion on the northwest embankment.
For this project, our group initially visited the site location with our community partner. We then acquired available information, including structural plans, hydrologic data, geotechnical borings, and spatial survey data. We then performed a structural analysis of the substructure, then investigated hydrologic conditions near the bridge abutments and estimated the flow of the upstream drainage area. Geotechnical analysis was then performed on the available test data to determine the strength of the soils. Different design alternatives were analyzed to help mitigate the scour-critical status of the bridge. Sustainability was taken into all design considerations. Costs were estimated for each design alternative as well before the final recommendation was decided upon.
Our design includes 3 alternatives, which consist of a fuse system, a relief culvert, and underpinning. A fuse system involves purposely designing a bridge's embankments to fail during extreme storm events in such a way that saves the rest of the bridge structure. During extreme storm events with high flows, the fuse quickly erodes away and provides additional cross-sectional area available for flow. This additional cross-sectional area significantly reduces flow velocities and correspondingly the stream's capability to scour the abutment foundation. The second design is a relief culvert, which involves strategically embedding a culvert in a bridge embankment to provide additional cross-sectional area during high flow events to reduce the water velocity. Culverts can be easily installed and represents a more conventional approach to remediate the scour problems with the bridge. Lastly, underpinning is a process that adds support to existing foundations by transferring loads in the deeper layers of soil. Underpinning could be used to add scour protection to our project by extending the abutment supports into a layer of soil outside the estimated zone of scour. 2 ways to accomplish this were investigated and include micropiles and helical anchors. Micropiles are drilled, grouted, cast-in-place, reinforced piles. They can be installed in confined spaces and difficult geologies with minimal disturbance to existing foundations. They become more expensive as the length of the pile increases, and numerous piles would be required to provide the necessary support. The other form of underpinning investigated is helical anchors, which provide both tensile and compressive support, can be installed in confined spaces, and have low mobilization costs due to small and relatively inexpensive installation equipment.
After careful consideration, taking into account cost, constructability, and feasibility of all of our design alternatives, our team has decided to implement a fuse system. The system can be constructed and repaired in a timely and inexpensive manner. The fuse also significantly reduces scour and allows for debris passage, making it the most appealing and sustainable design alternative.
We would like to thank our advisors, Dr. Mandar Dulkar and Dr. Andrea Pierce, for their help and guidance throughout this project. We would also like to thank our community partners, Carolyn Carlson and Jonathan Griffin of VTrans, for taking the time to show us the site and providing us with necessary information and data pertaining to our project. Additionally, we would like to thank South Mountain Research and Consulting and Malone and McBroom for their detailed report, providing us with further information for our model. Finally, we would like to thank the University of Vermont College of Engineering and Mathematical Science for providing us the opportunity to work on this service learning project. Thank you for your time.